Hey everybody, my name is Ricky and I'll be presenting on a paper called Convex Learning with Invariances today by these four gentlemen. First, I'd like to give you a roadmap. I want to give you the big idea in English. Why are we doing this? What's it for? Then I'd like to show you the experiments they ran. Then I'd like to get into the math and the algorithmic implementation. So let's just start off. What's the big idea here? So hold up your hand, right? Turn it around, move it, translate, whatever you want to do with it, right? You always recognize it as your hand. It's almost a silly question to ask because we do it so effortlessly, right? But as we've seen throughout this semester, and especially in our last homework, it's not actually easy to teach a computer how to do this, right? How do you recognize an object as the same object if it is in a different position, right? And so the authors really wanted to put this question on solid mathematical footing. There had been some research done before them on this topic, but they weren't particularly happy with it for one of two reasons. Either the research before them forced you into a particular mathematical form that you had to put your problem in, or it came up with a more general form, but it wasn't a particularly efficient implementation. You either had to generate too many examples or the search space was too large and you just didn't really want to sit around and wait for it. So what their goal is to provide the most general framework that they possibly could that could also be efficiently and scalably solved given these invariance transformations. So now we're going to jump into the experiments actually. I just want to show you what they did first. So they did two experiments. One of them was handwritten digits, classic MNIST. And the first thing that they did was they came up with 22 different translation functions that could potentially be applied to an image. A few of them are visualized here: translations, rotations, shears, that kind of thing. And with these 22 transformations in mind, they went and trained 3 different SVMs. The first SVM was just your garden variety standard SVM in black. They had 5 different sample sizes indicated by the points. They did 10 digits, 20 digits, 30, 40, and 50 digits per digit class. So 500 in total for the 50 digit per class. And then they trained up 3 SVMs. The standard SVM didn't do that great in accuracy, but it did fantastically on the right there in number of support vectors. The first answer to this came from previous research. The second SVM they trained was called a virtual SVM in red there. Now the virtual SVM essentially takes all 22 image transformations, it applies them to the training set before the SVM gets trained, it tacks on all of the image outputs to the training data, and then it trains the whole SVM on everything, right? Which is why it gets much better accuracy because it's got more data. But if you look over on the right there, it's got an obscene number of support vectors. And that was one of their problems with scalability. So they proposed this Invar SVM, the invariant SVM, as you can see, does much better or the same as accuracy-wise as the virtual support vector, but it cuts the number of actual support vectors in half. And it does this by basically intelligently searching for margin violators so it doesn't have to take into account all of them. So the second experiment they did was a spam filtering experiment. They proposed this algorithm called F-scale. It's a computational recipe that searches intelligently for worst case margin violators. The full version is in the paper, but the quick version is here. Essentially what it lets you do is scale a word either up or down and make letter shifts up to a budget K. They performed this on the ECML dataset, which is just an email spam dataset from a competition in 2006. And they trained their algorithm with 3 different methods. One was their standard hinge loss, that was their baseline. Then they used their F-scale algorithm in 2 different settings. F-drop, which is a special case of their F-scale algorithm that was also used in a previous version of research, and then their actual F-scale algorithm, and did a comparison. As you can see, they bumped up their accuracy by about 10 points over the original one, 9, and did marginally better than the F-drop. So that's nice. We can show that we get a great accuracy bump with pretty efficient implementation of the algorithm. So how did they actually then go about and do this? So classic machine learning problem style, you have an input X and a label Y. The first difference is that we define a 2-input function that takes an input X and a label Y and maps both of those to a real number. You can think of this as kind of a compatibility score of how well does this label Y go with my input X. And then we actually define prediction as a maximization problem over those compatibility scores. So can I find the Y label that has the highest compatibility with my given X? In our case, our function, our f of xy, is going to be a kernel function because there's a lot of scalable optimizers out there for kernel functions, and 2, the authors just like kernels. One of the really important things to define is going to be this space S. So this space S is the space of invariance transformations. It is every transformation that you can apply to the input X that won't change the output label Y. A few examples are down below. You've got Viagra changed as a spammer would change them into things that we obviously recognize as Viagra, but the computer would not. And then we have a 6 off kilter by about 30 degrees. You can still tell that's a 6, even though it's a little off. But the computer would have a tough time doing that. So the second thing that we have to define is a special cost function. So our normal cost function in machine learning would be y and y bar. So it would take the true labels and the predicted labels and give us some values back. But for us, we actually want to have a cost function with y, our true label, our predicted label, on the actual transformed input. And then we also want to pass in the transform itself. Now, the reason that we want to do this is because some of the transforms will be too far away from the original input, and we don't want to penalize ourselves too highly for that. So 2 examples of that are below. Viagra gets changed into diagram in just 2 operations, an insertion and then a change of letter. And we don't want to penalize ourselves for that. Another one is a 6 getting rotated 180 degrees is now a 9. And we don't want to penalize ourselves too much for missing out on that. So now that we have a cost function that actually takes in our invariance transformations into account, we want to define this key C quantity here. This quantity is the worst case transformation that we could possibly find. So we want to search over the whole space of transformations. What is the transformation, when we apply the transformation to X, which transformation is the hardest to classify for our classifier? Now, that's a little difficult because there's one problem with this, right? We don't have any guarantee on the form of C. We have no idea what C looks like. It could be the wiggliest function ever with tons of local optima, and that really defeats the purpose of scalable solving that they were going for. So what the authors then define is a convex upper bound on the worst case transformation. So I want to break this down for you guys a little bit. The first thing that you see is that the delta function comes almost directly down from the big C cost function, except we have one more, I'll call it degree of freedom, where we're searching over both the labels and the transformations. The search label gets put in the delta function instead of the actual prediction and the invariance transform. And then the blue term there, represents the margin violation. So it is essentially our compatibility function applied to the transformed input and the label that we're searching on currently. Basically the difference between that value and the same thing with the actual label that we gave it. That value is then scaled by this gamma function. In the experiments, they set all of this to 1, but what it does let you do is basically give a relative importance to the margin violation with respect to the invariance insensitive loss. So if you don't want the margin violation to contribute too much and you want the invariance loss to really dominate this equation, you'd set your margin scaling as some fraction. You basically find the worst label transformation combination that your classifier could possibly encounter, and that is going to be your loss function value. So I want to point out 2 important function properties. One is that the loss function is always convex, which means that we can scalably optimize it with whatever convex optimizer we feel like. It's proven by this first underlined blue equation here. It basically shows that the loss function is linear in F, and so we'll always return a convex function. The second important function property is that the loss provides an upper bound on the cost function that we actually want to optimize, and that's shown in the second blue underline. The delta y star s star term is the same on both the right and left side of the inequality. And this underlined blue term is always guaranteed to be positive because gamma is always positive. So an extra term added to the same thing will always make that inequality constraint hold. So now we're going to jump into the real math. Learning algorithms for minimizing this loss. If you are in 517 and remember back to the beginning of the semester, they formulate this as a structural risk minimization problem, where their risk is the sum of all of the losses plus the regularized norm of the function in Hilbert space. And then they derive the dual form of the equation from this. The dual form is immediately terrifying for these reasons. We have a 6-dimensional sum and a rank 6 tensor to actually deal with in computing our values. And this sounds just large, right? It sounds a little bit incomputable. But the 2 nice things that we do get from this is first, these 2 Lagrange multipliers here indicate to us that we have a quadratic program, which there are tons and tons of libraries to solve for us. And the second thing that we get is this nice form for our function f, our compatibility function. We get it in terms of a single Lagrange multiplier and then 2 kernel functions, the difference between 2 kernel functions. So as long as we define a kernel function and optimize over A, we'll be able to know everything for our compatibility score. So back to the 6-dimensional sum in the tensor. If you actually wanted to calculate this, this is the equation to do it with. The kernel has 6 indexes, which can be grouped into 2. Each group is one term of the inner product and one gamma term. Each term of the inner product is essentially the feature map applied to the transformation of the input x, and the y label that is at the current index subtracted off from the actual y label from that transformed input. You do that twice for both index groups, then you take the inner product of those, scale them by the gammas. This is just not a computable thing. You could write a 6 deep for loop to try and go calculate all of these, but it's just, even if you could store it, it's just not something you want to wait around for. And this is where the algorithm comes in. They devise a cutting plane algorithm, which actually goes one observation at a time to iteratively optimize and reduce the feasible region until it finds an optimum. So to do this, the first thing that we actually have to do is to define a working set of constraints for each observation. So each observation, if we have, let's say, 500 observations, we're going to have 500 different working sets of constraints. And then in each constraint, in each iteration of the for loop, what we're going to do is define our learning function. So this is that nice form of f of x that we just got from solving the dual program. It is the Lagrange multiplier times the difference of the kernel functions. The one big difference here from the formula that we presented earlier is that for the sum over the SY pairs, you actually only consider the SY pairs that are in the current working constraint set of the current observation. That's just a function. That actually is not any computed value or anything. That is just a function placeholder that we're going to use in the next 2 lines. So the next 2 lines actually compute something. So if you'll notice, what's inside this argmax here is actually our loss function, the LXYF that we were looking at earlier. And now that we have our compatibility function that we just defined in the line above, we can use that compatibility function in our loss function with the gamma and the delta function to actually go search over all of the transformation label combination pairs in that argmax S and S, Y and Y. It will search over all of the combination pairs to give us the maximum, essentially the worst possible transformation that it could find, given, of course, the current working constraint set, because that f of xy function will only go over the current working constraint set. This thing is called a cutting plane. It finds the cutting plane because later, as you can see in the algorithm, there's a potential for this to get added to the working constraint set. And if this gets added to the working constraint set, visually what it does is it collapses the feasible region of the optimization problem. So in 3 dimensions, just visually as a picture there, it will cut a hyperplane through the search space, the optimization space, and it will be smaller on the next iteration. So that's the first thing that we have to compute, the optimal transformation label pair, optimal meaning most margin violating. So the second thing that we have to compute is the current slack variable. So disregarding the optimum that we just found and only looking at the current working constraint set for the current observation, what is the worst margin violation we have so far. That comes out in the current Slack variable. I believe that's psi I. And then we have to compare the two values that we just computed. So we take our loss function with the S star Y star optimum that we just computed. We plug that into our loss function. And if that loss function value is greater than the current Slack variable plus the epsilon tolerance that we allow, that means that the S star Y star pair that we just found is a worse constraint violator, a worse margin violator than the current worst margin violator that we have. That is this if statement right here. We need to check to see if it is worse than the worst current violator that we have. If it is, we then go add it to the constraint set. We optimize again, and then it keeps going for each example, and then for each, it basically continues until the constraint has, the constraints stop changing, and that is the optimal solution. So there's another, that was the SVMstruct variant. There's another algorithm in the paper that I'm going to go into significantly less detail in. Basically, this algorithm performs stochastic gradient descent on the regularized version of the loss. It uses a learning rate 1 over lambda t, and then it projects the current weight vector back into the feasible region if it needs to, with that if statement at the bottom there. This is just another way of solving the same problem. It uses the actual original risk functional that they define, and it's essentially just another way of solving the problem. So equally as efficient. So in summary, I'd just like to make a few points. So the incorporating invariances really helps the algorithm, especially on small data sets, in terms of accuracy really. The invariances, the authors showed that invariances can be formulated as classic convex optimization problems for any choice of the things that you need in the equations, which means that they achieved their goal in actually doing efficient optimization. And then the cost function is basically looking for the worst case margin loss every time. And it only relies on finding the worst case invariances. So if your space of invariances is infinite, right, you don't need to search through the entire space. All you need to do is actually find the worst margin violator, and that will be enough for the algorithm. And so with that, I thank you guys for listening, and I hope you have a great day.